Okay, so I want to start with something that kept popping up in the stack of documents for today. It's this one metaphor.
Let me guess. Greenland.
Greenland, exactly. And it feels like such an odd place to begin when we're talking about healthcare and technology, doesn't it?
It really does. But it's actually the perfect framing device once you understand the source. We're not talking about the country.
No, not at all. In these military strategy documents,
Hmm.
Greenland is their sandbox. It's for testing something called network-centric warfare.
Right.
The whole idea is if you can connect every single thing, every sensor, every vehicle, every asset in a totally barren, hostile place.
Into one unified grid.
Yes. Then you own that territory. You have total awareness.
And that's the connection. That's the core argument in the documents we looked at.
It is. They're saying the new battlefield, the new Greenland, is the human body.
That's the whole thesis right there.
Yep.
We're not just talking about the Internet of Things anymore. This is the Internet of Bodies. And it's so much more than just wearing a smartwatch. This is a fundamental shift. The industry has a name for it.
Healthcare 4.0.
Yeah.
Or the biodigital convergence.
Exactly.
So let's actually break down that architecture because some of the diagrams in these government docs are pretty striking. I'm looking at one from NIST, the National Institute of Standards and Technology.
Ah, the Cyber Physical Systems Framework.
That's the one.
It's a foundational document. It shows you how the modern world is wired together. You've got the power grid, smart buildings, transportation.
And then just sitting there in the middle of it all is a box labeled human. And it's treated just like any other node, like a thermostat or a smart car.
The term they use is a gray box.
A gray box, right. What does that signify in this context?
Well, in systems engineering, a gray box means you understand the inputs and the outputs, even if you don't know the exact internal workings.
So the human is just another component. It generates data, and it can receive commands.
That's the implication. And all that data it's generating, that's what leads to the next big concept.
The digital twin.
Right.
Now, I usually hear about digital twins in, like, aerospace.
Mm-hmm.
You build a perfect virtual copy of a jet engine, and then you can simulate 1,000,000 hours of flight to see where it breaks.
It's predictive maintenance,
Yeah.
pure and simple.
But these sources, especially the papers from Siemens Healthineers and The Lancet, they're applying this to the patient in silico.
This is the big goal of Healthcare 4.0, to create a living, breathing simulation of you.
So not just a static PDF of your medical history.
No, a physiological model that is constantly updating. So if a doctor wants to try a new drug, they don't have to risk giving it to you first.
They test it on your digital twin.
They test it on your twin, see how it responds, and then they make a decision.
Okay, that sounds amazing in theory. But to build a simulation that accurate, you'd need a constant fire hose of data. A checkup once a year isn't going to cut it.
And that's where the infrastructure has to change. To get that fire hose, you need something called a WBN.
A wireless body area network. I was digging into the IE standard for this, 802.15.6. And what struck me is they make a big distinction between wearables and something they call intrabody communication.
That is a critical distinction, and it's one most people miss. They just assume your pacemaker or whatever is using, Bluetooth, sending radio waves through the air.
But radio waves are actually terrible at going through the human body.
They are. The body is basically a bag of salt water. And salt water is conductive, which means it blocks RF signals really, really well.
It's like a Faraday cage.
A partial one, yeah. So trying to send a signal from your chest to your ankle with standard radio requires a lot of power, and it generates heat.
So the solution detailed in the sources is to, well, stop fighting the body's physics and start using them instead.
You become the wire.
Literally. Intrabody communication uses your own tissue as the transmission medium.
It's far more energy efficient, and it's also more secure in a way because the signal doesn't just radiate out into the room for anyone to pick up. It stays inside the human internet.
Although, if my skin is the firewall, what happens if I touch something or someone?
That's a real vulnerability. It's called capacitive coupling. Data could theoretically transfer on contact. But what's really fascinating is the kind of data these sensors are collecting. It's a whole taxonomy of biosignals.
Yeah, it's not just your heart rate. The National Archives documents list things like gait analysis, respiration, and even body noise.
Body noise, which sounds so vague.
But it's not. It's the acoustic signature of your internal organs, the sound of your heart valves opening and closing. It's biometrics on a completely visceral level.
And you have to remember, while we might think of this as sci-fi, the Federal Register already lists these things as established tech for remote patient monitoring. The rules are already on the books.
Okay, so that's the network side, how you get data out of the body. But then the sources take this really sharp turn into replacing silicon with biology, this whole section on wetware.
We're hitting a wall with traditional computing. It's fundamentally an energy problem. Everyone loves what models like ChatGPT can do, but nobody talks about the cost.
The data centers.
The massive data centers, they consume megawatts of power and millions of gallons of water just for cooling. It's just not sustainable.
There was a comparison in the material that was just staggering. It put the frontier supercomputer up against the human brain.
It's a very humbling comparison. Frontier weighs tons. It takes about 21 megawatts to run. The human brain weighs 3 pounds.
And runs on what, 20 watts?
20 watts, barely enough for a dim light bulb. And yet, both of them operate at exascale speeds. Biology is just a radically more efficient computer.
So the industry's looking at this and thinking, don't just build better chips.
Use better hardware, use biology. And this is the field of organoid intelligence. The sources highlight companies like Cortical Labs.
The dish brain people.
Right. They're taking human stem cells, turning them into neurons, and growing them directly on a silicon array.
They call it the CL1 system. It's basically a brain in a box.
And these neurons aren't just decorative, they are the processor. They're running what they call a biological intelligence operating system, a BIOS.
That is just a complete redefinition of hardware. But it gets even smaller. The sources talk about DNA computing. And the liquid DNA computer sounds like pure science fiction.
It sounds like it, but the mechanics are all chemistry. See, a silicon chip processes things serially, one bit at a time, just very, very fast.
But DNA computing is massively parallel.
Massively. You can put trillions of DNA strands into a single test tube, and when they react with each other, A bonding to T, C to G, that chemical reaction is the computation.
So you encode a math problem into the DNA itself.
Yes. And as the molecules just naturally find their partners, they are literally solving the equation. The answer is the final molecule that's formed. It's like a biological computer that programs itself.
Okay, so we have the networked body. We have biological computers. The piece that's missing is the interface. How do you connect the digital world to the biological one without, drilling holes in everyone's head?
That's the real barrier to entry. Something like Neuralink requires invasive surgery that's never going to scale to the whole population. So the future, according to these MIT papers, is something called circletronics.
The scale of this is what got me. They're talking about devices 1/billionth the size of a grain of rice.
A speck of dust. You can't even see it.
And you can inject it. But the delivery system, it's like a Trojan horse.
It is. They don't just hope it floats to the right spot. They attach these little bioelectronics to your own immune cells, monocytes.
Which are programmed to do what?
Hunt for inflammation. And, crucially, they have a security pass. They can cross the blood-brain barrier, which is normally impenetrable.
So your own immune cell smuggles the chip into your brain. But once it's there, how do you power it? A chip that small can't have a battery.
It can't. And this goes back to DARPA's electronics program. Electrical prescriptions, they use something called neural dust.
And since radio waves don't work well deep in the body,
they use ultrasound. An external device sends out an ultrasonic pulse, which makes a tiny crystal inside the dust vibrate.
Piezoelectricity.
Exactly. That vibration generates just enough voltage to power the sensor and send a signal back out. No wires, no batteries.
But ElectRx, it's not just for reading signals, is it? The program talks about closed-loop neuromodulation.
That phrase, closed loop, is everything. It means the system is autonomous. It can detect a problem, say a pain signal or a stress response, and it can automatically fire a counter signal to the nerve to suppress it.
An automated thermostat for your nervous system.
Precisely,
Right.
Which is where the anxiety comes in. The sources connect this to a directive on autonomy in weapon systems. They call it wireless drugging.
Because if a system can just turn off fear or pain in a soldier.
It bypasses choice. You aren't calming yourself down anymore. The software is.
And if this is all happening on a network, we need to talk about that network. Because connecting one person is one thing. Connecting everyone is where you get the IOBNT.
The Internet of Bio-Nano Things. This is research out of places like Stanford. They're looking at how to get cells to talk to each other.
Using a virus, of all things.
The M13 virus, yeah. But here, the virus isn't a pathogen, it's a data packet. They engineer it to carry a genetic message from cell A to cell B. It's basically Wi-Fi for your cells.
But a cell can't talk to the internet directly. How do you bridge that gap between the wetware and the global fiber optic grid?
That's the backhaul problem, and the solution the sources point to is Well, it's quantum, work being done by IonQ and the Air Force on ion-photon entanglement.
The universal translator.
It is. It can take a signal from a biological quantum-level system and convert it into a telecom wavelength photon, light. Light that can travel through a standard fiber optic cable. It's the bridge.
The bridge that lets the biological internet plug into the global internet.
And once you have that, you can connect everything. The smart dust in the air, the sensors in the roads, the people walking through the city, it all reports to the same system.
It's the Greenland doctrine, fully realized.
Total connectivity.
Okay, but most of us aren't living in a DARPA lab. We're just trying to get our health records straight. But the sources say this is already hitting the consumer market.
Just with a much friendlier face.
ChatGPT health.
Exactly. OpenAI is rolling out these dedicated spaces where you can connect everything. Your Apple Watch data, your medical records, your 23andMe results, all in one place.
And, I mean, the utility there is obvious. The healthcare system is a mess to navigate. Having an AI that can look at all my data and say, hey, your trends are pointing towards prediabetes, that's powerful.
It's the patient in silico for everyone. And OpenAI is very clear that they don't use this data to train their main models. They say it's siloed.
But the sources bring up 23andMe.
It's a cautionary tale, isn't it? Millions of people handed over their genetic code, and then the company turned around and sold access to that database.
The argument is that when you gather the real-time biological data of hundreds of millions of people,
You've created a honeypot, an asset that is almost too valuable to remain private.
and it trains us. It normalizes the act of feeding our biology into the cloud. We become nodes.
We do it voluntarily, through convenience, not coercion.
So if we bring this all full circle, we started with the body as territory. We've looked at the maps, the NIST diagrams. We've seen the infrastructure with W-bands and the new hardware with wetware.
And the interface with Electri-X, when you put it all together, the line between human and machine, it's just getting blurry. It's becoming a semantic argument.
Human-machine symbiosis.
That's the term. And it has huge implications for autonomy. If my nervous system can be read from and written to by a closed-loop system, where does I begin and the network end?
Our laws are built on the idea that your body is a closed, sovereign system.
But what if it's not? What if it's a node on the internet of everything, getting software updates you didn't approve? Do you still have admin rights?
The firewall is down.
The firewall is down. And the network we've been talking about, it's not some far-off future. The 5G, the IE standards, it's already built.
We're just waiting for the apps.
It definitely makes you look at that accept terms and conditions button a little differently.
It should. Because in Healthcare 4.0, the user isn't just using the platform.
The user is the platform.
A lot to think about. So what's your take? Are you ready for the upgrade? Or are you trying to stay offline?
I'm just not sure offline is going to be an option for much longer.
Thanks for diving in with us. We'll see you next time.